about black holes, and I'll tell you a bit about how we see black holes and then how we listen to black holes, which is my favorite part. Let me see if we get our slides here. The first slide has the title, Einstein, black holes and gravitational waves. That's the mysterious part. There it is. Okay, so let's start with Einstein, because that's how black holes started, at least what we know about black holes. Now, this needs to work. It worked before. Oh. Okay. Okay, so Einstein's theory of general relativity is actually a theory of gravity. It replaces Newton's theory of gravity. Newton's theory of gravity told us that the Earth goes around the sun and satellites move around the sun because there is this force of gravity that attracts masses and planets and all of us together. It's nice to think that we all attract each other. We all have positive mass. However, Einstein didn't like this because that meant that there was an instantaneous force, and he had come up with this natural speed limit, the speed of light. So what he said is that masses, actually what they do is not, they don't attract other bodies, other masses, but they curve space-time. So you have to imagine space-time as a grid that if there is no mass, it's a grid with equal length among all corners and a little clock in each corner, and it's all synchronized. But if there is a mass, then space-time is deformed. And then distances become shorter in some directions, longer in others, clocks become desynchronized, and that is what actually makes bodies move around each other. It's that deformation of space-time what makes the Earth go around the sun. So everything you learned about Newton's gravity was wrong. It's approximately right.
Pretty good approximation, most.
Good enough for government work.
Yeah. Good enough for government work. He was working for the patent office, so. A consequence of his theory of gravity, this general theory of relativity, is that if you have mass, if you have particles, and you don't have atoms, you don't have electric forces, you don't have quantum mechanics, you only have general relativity, then all the mass is going to collapse together in a black hole. All the mass is going to come up in a single point that's going to be what we call a singularity, and it will have a horizon around it, and that's a black hole. Now that sounded too mysterious, not just to Einstein, but to every astronomer at the time. They didn't believe in black holes. They thought that this was an awkward feature of the theory. But it turns out that they do exist. Now we know better. And if this is a deformation in space-time that our sun has a mass that we call one solar mass, just to make it simple. You know that the mass, the sun is very, very large. It's about 100 Earths. It has a diameter that's about 100 Earths, 200,000 miles. If that amount of mass gets compacted into a black hole, it will be a tiny black hole that has 1 mile diameter, about 1 mile diameter. 1 mile from 100 Hertz, all the same mass concentrated in 1 mass. But if the sun became a black hole, the Earth would not be swallowed by the black hole. We don't have to be afraid of black holes. We would be a lot colder, but the Earth would go around the black hole, which was the sun, with the same radius, because it has the same deformation at the same distance. If it has the same mass, it has the same amount of gravity force, if you want to call it force. There are other objects that are almost as dense as a black hole. These are the densest objects, and they are called neutron stars. And they are, like I said, the most compact ones, and they have the mass of the sun, but concentrated in a very small radius, not as small as a black hole, but about a 6-mile radius, which is about the distance, I looked it up today in Google Maps, from LSU to Our Lady of the Lake, or the Mary Perkins Cancer Center. So that's black holes. Now, why are they called black? Because light, neither light nor anything can escape from a black hole. If something falls into the sun, if something falls into the earth, it can get out again. It just has to fly very, very fast. You have to find a very, very fast rocket to get out of the earth, and even faster one to get out of a star. But if you are inside a black hole, if you fall inside a black hole, you can never get out, because if you wanted to get out, you would have to travel faster than the speed of light. So they're called black because no light can escape. We cannot see it. We cannot get light from black holes like we get from the stars. And that's the whole reason why we call them black. Why is it a hole? That's another story. Now, how do we know, how did astronomers know that black holes actually do exist? If we cannot see them, we don't get light from these like we get light from the stars. Well, it turns out that one of the reasons we can learn a lot about black holes is that many black holes are in what we call a binary system. They are dancing what I like to call a tango, because I'm from Argentina. They're dancing a tango with another star. This is, for example, a blue star that we call Cygnus X1, or the region. And that star we can see, and if you look at the light from the star, actually we can tell that the star is moving just a little bit. And that's because it's orbiting something else that we don't see. And that something else is a black hole. But we do know more than that, because particles from the star that are falling into the black hole are falling very fast. And when particles move very fast, they do radiate energy, and we can see that in the X-rays. And sometimes we can see even flares in X-rays from here. This is an X-ray image of the same region, so this is what we think it's falling into the black hole, and this is the light in the optical spectrum that's emitted by this blue star. So we do know that there are black holes. We also know how they start. They can start when a supernova explodes. You probably have heard about supernova explosions. There's certain kind of supernova explosions that are called core collapse supernova, which happens when stars are a bit less than 50 solar masses or so, and they explode in such a way that their core ends up collapsing. That's why we call them core collapse supernova, and they leave behind either a neutron star or a black hole. But the black hole is kind of small because a lot of the mass went away. And the neutron stars, we know, have a mass of about the mass of the sun. So they're also kind of small in astronomy standards. So we know that happens, and we also know that if we have two of these neutron stars together, and many stars like to be in binary systems, they are going to get closer and closer together, because some energy is going away. I'll tell you more about that later. And when they get together, they form a black hole, but they also emit a lot of light. And we have been seeing some of these light. It's not actually light, it's gamma rays, but we have seen the bursts of gamma rays that we think come from these explosions, from these collisions. And if I had time, I would give you another talk about that movie, which is made about an event that we discovered, but I'm here to talk about black holes and not neutron stars. Some black holes, however, are very, very large. They start small, but somehow they become large, especially at the center of the galaxies. This is the center of our galaxy, And you can follow the trajectory of stars if you're very, very patient. You have probably not been looking in here, but this movie started in '93. It's now 2015. And it took that many years to see these stars going around in different trajectories around this point that is not emitting any light. Sometimes it emits flares of X-rays, but it's not emitting any optical light. And that's how we know not only that there is a black hole in there, but we can weigh the black hole, because just like we know the planets move around the sun, and that's how we know the mass of the sun, we can actually tell from the motion of these stars how big is this black hole at the center of our galaxies. And it has 4 million times the mass of the sun. Remember I told you that black holes started small, but somehow if they get to the center of galaxies, then things keep falling and falling into them and they become very large. In fact, our black hole at the center of the Milky Way is kind of small. Ours is on the low side for black holes. Most black holes at the center of galaxies, and now we think that every galaxy, or almost every galaxy, has a black hole at the center, and they are millions, sometimes billions of solar masses. We call those supermassive black holes. The regular ones, they're massive black holes. So we have names for those. Now, if 2 black holes get together, we don't see anything. They will, the theory tells us that they will get closer and closer together and merge into a single black hole. If we are close enough, we might see some distortion of the stars around them. That's distortion of the light coming to us, not the motion of the stars themselves. But we don't see any light coming from the black holes. What Einstein's theory tells us, though, is that this merger is producing distortions of space-time. Remember that gravity, the gravity force between these black holes were distortions of space-time, curvature of the space-time. So if the black holes are moving, then there are these ripples of space-time that are being produced. Now, how do you measure those? Those are not light. You don't need, you can't use a telescope. You have to measure distances or times very, very, very precisely. And actually, when Einstein put numbers in this, which was just 1 year after he published the theory of relativity, he had a paper on gravitational waves, and he said, that's impossible to measure. He went on to look for other effects that could prove his theory had been measured. This was way too small. And people 50 years later thought that they were too small. But it was about that time, in the 70s, when people said, well, we could use interferometers. Interferometers are instruments that with a laser light measure the difference in distances in 2 perpendicular arcs. Light is a wave, so if we have this laser light moving that way to a mirror and then getting reflected and then getting bouncing again here in the beam splitter, so we have 2 waves coming out, and if these 2 distances are the same, then the 2 waves cancel each other. But if they are not the same, which is what would happen if there is a gravitational wave going through, or if the ground is moving, like when we drive too close, then the interference at the output will not be destructive, and we will see some light. So if we put a photodiode right here, and we measure how much light there is in there, and we see there's more light, less light, more light, less light, that means that the 2 distances are changing, and if we know it's not happening for any other reason, like I said, tracks or logging tracks or seismic motion or quantum noise in the light, all those things are things we have to take care about, then we can tell there is a gravitational wave. Now these gravitational waves, like I told you, Einstein told us, are very, very, very small. So small that if those 2 black holes I showed you with about 30 solar masses were about 1 billion light years away, which is relatively close for astronomy standards, then this distortion of distance would be not just smaller than an atom, not just smaller than a proton, but smaller than a part in 1,000 of a proton. And that, if you get to make the arms long enough, they would have to be 4 kilometers long for you to measure that huge distance of 1,000th of a proton. So that sounds impossible, but that's what you all did. You, paying taxes, helped us build, through the National Science Foundation, not just one, but 2 observatories, 2 interferometers, each one 4 kilometers long. And one is in the state of Washington, in the middle of the desert, and the other, it's only a 45-minute drive from here. How many of you have been to LIGO? And shame on all of you who didn't raise a hand. This is only 45 minutes drive away. There's an open house every 3rd Saturday of the month afternoon, April 21st, I think it's the next one. So go and see it. It's actually a lot of fun, more than I can describe. But these 2 detectors began to be built in the 90s, were operated in the 2000s, not with enough sensitivity. In 2015, we were beginning to operate a new version with better sensitivity. And on September 14, 2015, less than 2 years ago, so this all started in the 70s, it took a lot of years, a lot of patience, but in 2015, we saw this. And this may not mean much to you, but let me explain. The blue trace, which is an amplitude as a function of time, and this amplitude is how much these 4-kilometer lengths changed with respect to each other, divided 4 kilometers. So 10 to the minus 21, this peak in here, the tick mark, is 4 thousandths of a proton. That kind of distance is what we are measuring here with this blue trace, which comes from the photodiode at the LIGO Livingston detector. And this orange trace is what comes out of the Hanford Observatory, which is 3,000 kilometers away, on the other side of the country. And these 2 photodiodes, with only 7 millisecond difference, measured the same trace. And that trace is like a sine wave, but not just any sine wave, it's a sine wave that grows in amplitude, grows in frequency, and then dumps down. That's exactly what we expected to see from the coalescence of black holes. So not only we got the first detection of gravitational waves in 2015, and that made us really happy. I can't tell you how many times, how many bottles of how many drinks we opened. But it was amazing. But it was from black holes, the most mysterious objects in the universe. This is just a picture of our group of students, young people in our group at Livingston, celebrating the day of the announcement, while a few of older professors, including myself, were in Washington making the announcement. That was actually, can we go back? That was, this is Ray Wise, an adjunct professor here at LSU. He's emeritus professor from MIT. He's the one who started proposing these interferometers long time ago. And he's coming to give the commencement speech on May 11th. He's also recently a Nobel Prize together with Kip Thorne and Barry Barish. So that was quite an honor. Now that was the first gravitational wave. Since then we have discovered several others. We have discovered 5 gravitational waves from black holes, but the second one was significantly different than the first one because it came from smaller black holes. So bigger black holes produce lower tones, lower frequencies, higher black hole, lower mass black holes produce higher frequencies, higher pitch. So we like to compare those, and we like to put them on speakers. That's what the long one sounds. That's what the short one sounds. And that was very disappointing. So what we did is we used false sound. We added 400 hertz. And it sounds a lot better. Now this is cheating a bit, but we learned that from real astronomers who put all these X-rays and ultraviolet in reds and blues, so we don't feel so bad. This was done by the LIGO and Virgo collaboration, a big group of people. So I told you that we have discovered several coalescences of black holes now, almost as many as we know about from these X-ray observations. And we are learning more and more about this. We are improving the sensitivity of our detectors more every year. So this amount of data we have about black holes, not just by themselves, but in pairs, forming bigger black holes, it's a treasure of information. We call this the new gravitational wave astronomy. Now, for bigger black holes, we can only measure the small black holes, what we call stellar mass black holes, perhaps up to a few hundred solar masses, but not the big ones at the center of the galaxies. For that, you need to make interferometers much longer. So there's a project called LISA that puts 3 satellites in space and sends a laser among the satellites. The satellites are 1 million kilometers apart. Well, they will be. It will launch in 2034, so it's going to take a while. But when it launches, then that interferometer will measure gravitational waves from massive black holes. And if you want to measure the supermassive black holes, then you need an interferometer of galactic scale. And we can do that by getting light, measuring light from different stars in the galaxy and measure the difference in phase. So we can make the galaxy an interferometer. That's all coming next to you. And this is what we call gravitational wave astronomy. Thank you. And I always run over time, but maybe there's time for 1 or 2 questions.
Oh, absolutely. We have plenty of time. We have plenty of time for questions. So at this time, we would love to take questions about Gabby's talk. Unfortunately, you're just going to have to yell it out at us, and then we'll repeat it, because we can't, unfortunately, get mics out to you guys. Hey, hello.
Hey, what causes the difference in frequency in the gravitational wave astronomy things? Like, why do they always spike up?
You see them in that color diagram, you see them going up because they go up in frequency. As the 2 masses get closer and closer together, they're moving faster, so that's a higher frequency. However, the lower the mass of the stars, then the larger the frequency, the last frequency you can see. I don't know who's...
A lot of guys who go from in the 90s not being able to very much, and in the early 2000s not being able to differentiate signals to finally getting where it needed to be.
What allowed us to improve the sensitivity since the very early times to now? Very hard work. Actually, it was already in the 70s, the interferometers were designed as a possible way of doing this. In the 90s, the projects were approved, and even in the 90s, they said, well, the first generation technology detectors will probably not detect gravitational waves. We just need the proof of principle, and then we can install better technology that will do it. And that's the way it happened.
Please.
Is the only reason that we didn't start building interferometers in space because we did the first concept before?
Why don't we have interferometers in space yet? Actually, at some time we thought that we were taking so long with these interferometers on the ground that we thought that the ones in space would be first. But they are very expensive. They are on the ground. You can spend a little bit at a time. You take the time to build them up, to improve them. In space, you have to put all the money in the bank and then launch it and then have it right the first time. You only have one shot. So it's difficult to convince funding agencies to do that.
Yes.
How often do two black holes merge, and how do you know to be looking at them, at the right time to catch them?
Oh, these are all very good questions. Actually, we didn't know how often these things happened. The question was, how often do black holes merge and how do we know where to look? We didn't know how often black holes happened. We kind of knew how often neutron stars merged, and we have only seen one. I didn't talk about that, but we have seen one of those mergers. Very recently, that was the last thing we saw. But for black holes, we had no idea. The predictions were varied by orders of magnitude. So now we can tell, we just measure from our observations. How did we know where to look? Well, it turns out that one detector, each of these detectors, and we have 3 now, there's another one in Europe, are like microphones more than telescopes. So they can hear signals, almost literally, from almost anywhere around the space, even below the Earth, because the gravitational waves go straight through. So we don't have to point.
So if it's possible you could have built this thing and had to wait 1 million years for black holes to merge?
It would have been possible. There were predictions that black holes never form binary systems. They were never enough to meet in binary systems like this. So one of the predictions was 0. We proved that wrong. But it was built not so much to look based on the prediction for black holes, but on the predictions for neutron stars, because those are much safer predictions.
We got time for one more question. Sir.
Why do the 2 black holes that are orbiting each other fall in toward one another instead of just continuing to orbit?
That's also very good questions. They do that because as they are moving, they are distorting space-time, and those ripples of space-time are traveling at the speed of light and carrying energy away from the system. So according to Newton's theory of gravity, if you have 2 masses orbiting around each other, they will do that forever. If you have Einstein's theory of gravity, then there is this space-time effect, this space-time energy that's being taken away, and then the stars have to get closer and closer to each other. And that was proven actually long before we had our detectors. There were measurements, astronomical measurements, radio measurements of neutron stars that proved that the neutron stars were getting closer together, just like Einstein predicted.
Thank you guys so much for coming, first of all. I hope you're all having a good time.
Yeah!
As Tyler said, today I'm going to be telling you guys about the science of the film Interstellar. How many of you guys have seen this film?
Yeah.
Yeah, a whole bunch of you. Excellent. So you're going to be able to understand the references. Yes, you love it. That's excellent. I also really like this film. So first of all, why the heck am I going to talk about this? This is a really unique movie for a very specific reason. Oh, sorry, you just keep it there. So normally when people make sci-fi movies, they have, a plot, they have characters, they have interactions, and then they build all of the science that they need into that story. But with this, they did it the other way around. So this guy, Kip Thorne,
That guy.
he's a very, very famous astrophysicist, and he's now even more famous for just getting the Nobel Prize. He was one of 3 astrophysicists who got it for the LIGO detections of gravitational waves.
Yeah.
So he and his good friend, Linda Obst, came up with the idea for the story in Interstellar and all of the physics within it before anybody else had signed on to this movie to work on it. And then after that, they got a writer, Christopher Nolan's little brother, and then Christopher Nolan himself to direct it, and all of them and their entire team of visual artists and people with very big computers were dedicated, heart and soul, to making the physics within this movie as believable as possible. So as much of it is grounded in real science as they could make it. And they did a really wonderful job. So let's start talking about the first science that you run into in the film. It's actually not astrophysics. It's about the Earth. So what we find out at the setting of the movie is that the Earth is becoming uninhabitable to humans. And what's happening is that there are giant dust storms that are starting to go all over the globe, and they are making crops die. Blight is killing them, and expelling nitrogen into the atmosphere. And the more nitrogen is, the less oxygen there is, which means it's becoming unbreathable for us. And as the crops die, I mean, what are we going to have left? Corn is the last thing that they have left in the film, and as they talk about later, even the corn is going to die eventually. So, what are our options there? Don't have a lot of them, not at present day. So one of the questions that you might be asking at this point is that really possible? Could this really happen to the Earth? And the answer is, it actually already has. So this photo right here is from April 14th, 1935. This is a small town in Kansas, in the middle of the Dust Bowl. And this probably looks really familiar to you guys if you've seen the movie, because there are scenes that look almost exactly like this. And this phenomenon of these giant dust storms was caused by sort of irresponsible farming methods in an age where more and more food was starting to be necessary because the population was really booming. And this issue was fixed as the dust storms were starting to move toward the Atlantic seaboard to Washington, D.C., where the senators finally decided, oh, we should probably do something about this. So they enacted the Soil Conservation Act, which helped farmers to put more responsible farming methods into their repertoire, and they rectified this issue before it became a really huge matter. And what we're finding out now is that this can repeat itself. So this other photo right here is from 2011. This is in Arizona. And other photos just like this you can find all the way up through 2017, 2018. This is happening all throughout the Southwest currently. And it's not because of irresponsible farming methods, it's for other reasons that have to do with climate change and the warming of the Pacific seaboard. So, I mean, this does happen, and if we don't do something about it within the near future, we're probably going to have some similar problems to deal with as they faced in the 1930s and as they're facing in Interstellar. So, what can we do about it? Well, one of the answers is we can leave Earth. And this photo over here is a very special photo. That is the Vostok 1 mission. And this was piloted by this guy, Yuri Gagarin. And today, 57 years ago, he was the first man in space on this mission. So all of you here tonight are celebrating with us Yuri's night. Which makes this film even more important for us to discuss. And in Interstellar, they have the same option. Their technology is even more advanced. So they actually do leave Earth. They go off and they search for other planets that might be habitable for us. They leave in this nice craft here, a little shuttle, and they go to this wonderful interstellar spacecraft, and it spins. Does anybody know why it might be helpful that it spins? Right, exactly. So it's just like if you were to spin a bucket of water around really quickly, the water feels a force outward. I mean, if you've taken a physics class, they probably tell you that this is a fictitious force. But in the frame, the reference frame of the water, it is a very real force. And it's the same force that the astronauts feel if you imagine that their feet are down here and their heads are over here. What they feel is an outward push this way. And if you spin the craft at just the right speed, you emulate exactly the gravity of the Earth. So really nice that they have a spacecraft that spins. And what their eventual plan is, if they can find a planet that works well enough, they want to use this craft to launch everybody on the Earth into space and escape the folly of their ways. So, where are they going to go? Where can they look for a new planet? I mean, as our protagonist Cooper says in the film, the nearest star that might have a planet around it, which we actually know now that they do, is about 1,000 years away from the Earth. And they measure it in years because that's about how long it would take us to get there at the speeds of our current spacecraft, or their current spacecraft. That's a really long way, right? I mean, by the time they even got there, who knows if humanity would even still be on the Earth anymore? They might have all gone extinct. So that's not an option, right? So where do they go? Well, thankfully, somebody, a very nice, beneficial somebody, has put a wormhole right where we might want it, within our solar system, around Saturn. So then the question is, what on earth is a wormhole? Why do we care about it? And to talk about that, I have to tell you guys about Spacetime. Thankfully, Gabby has done most of the hard work for me in describing Spacetime, so you probably recognize an image like this from her talk. The bottom line here, really, if you need a reminder, is that mass bends space-time, it stretches it near to the mass, and then that curve of space-time tells the matter how to move within the mass's vicinity. It's a really important concept. And another important thing is that it isn't just the space that bends, it's the time also. Now, this is actually an animation, but I don't really need it for you guys to see. But the main thing here is that these clocks toward the center of the mass, they will move slower. The seconds will tick slower than the clocks out here, further away from the mass. And that is an effect that physicists call time dilation. And that's really, really important later, so I'm going to get a little bit more into that later on. So, next thing about wormholes here is that if we squish the space down to 2 dimensions, you can get images like this that you also saw in Gabby's talk. And stars like the sun, they form a considerable little dip here, but the more dense the object is in space-time, the deeper this dip is. Okay? And then if you want to form a wormhole, what you want to do is you want to take 2 black holes, these really, really big ones, and then if you have a space that looks like this, fold the space over so that those 2 black holes touch. And then you get something that looks like this. And this image is really useful, but it's also wrong. See, this spaceship here is mass that exists within our 3-dimensional space, which means that it also has to be confined to that same 2-dimensional plane that we squished all of our stuff down to, right? So images like this are a little bit misleading, and they're a little bit of what causes other movies, other artists to depict black holes and wormholes as holes in space. You've probably seen them. I've seen a million of them. But if you really want to talk about what a wormhole would look like to us in reality, you have to talk about this shape here. This is a circle in 2 dimensions, right? What's a circle if you expand that into 3 dimensions? It's a sphere, that's right. So the wormhole in Interstellar is a sphere. It's a beautiful sphere. It looks even more beautiful up close. And they get even closer than that, right? They go into it. What does that look like? If you've seen the movie, then you know what it looks like when they go through the black hole, or excuse me, through the wormhole. But what it would really look like if it were this shape of wormhole, it would actually be quite boring. I mean, you see what's on the other side, and then you go into it, and what looks like it's a bit of a warped image of the space on the other side, it becomes sort of flattened, and then it looks exactly like it would look if you were already there, and then you are there. And that's it. It's not really all that exciting. So this is the one spot in the movie where the images that they show you in the film dramatically diverge from the real science. Does anybody want to see it? We can play this clip.
Yes.
Can we do this up there? We have somebody approaching the podium. Yes. In the meantime, I can show you some pictures of it, if you'd like. Or should I not spoil it? Don't spoil it, okay. I hear the audio.
The elevator, right? At least some of them. Say goodbye to our solar system, to our galaxy. Here we go. here. We're passing through the bulk. Space beyond our 3 dimensions. All you can do is record and observe. What is that?
It's
Distorted space-time. Don't!
And they're out. It's pretty awesome looking, isn't it? So to do that, what they did was they combined several different shapes of wormholes and then put a little bit of artistic rendering in there that they thought would be exciting. And it ends up being a really, really great show. It's beautiful. And the first handshake in there. You'll notice that they actually used a couple of words that maybe you didn't understand in the film the first time you watched it. They said the bulk, or passing through the bulk. So what that is, when we get back in here, I can show you what the bulk is. Yes, perfect, thank you. So the bulk is this area in between and on the outside of our sheet of space-time. So it's a 4th spatial dimension. So, I mean, if you're a human and you're looking at this sheet, then you're experiencing 5 dimensions, right? You're in the 3 dimensions that we have regularly. It'd be up and down, left and right, forward and back. And then time is a 4th dimension, and then you have another spatial dimension. And that's the stuff outside. That's the bulk that they're talking about. So when they're talking about the wormhole and they say we're passing through the bulk, that means they're going through this throat here, the throat of the wormhole. So what's on the other side of the wormhole? We've talked a lot about the wormhole itself, but let's talk about what's on the other side now. Some images of the wormhole inside. So, oh, actually, I wanted to talk about one more thing, an important thing that's relevant, especially from Gabby's talk, and that's how we detected the wormhole. So, on the other side of the wormhole, some stuff happened. There was a cataclysmic event. This is something that Kip Thorne talks about when he does this talk, The Science of Interstellar. He has an entire book on this, and I haven't had a chance to read it, but I saw him. I had the chance to actually see him give this talk in Ohio. And he does talk about what caused this detection here. And you have some kind of an event that releases a lot of radiation and a lot of gravitational radiation. And what that does is it produces gravitational waves that start, say, if the event happens around here on the other side, and the Earth is up here on our side, then what happens is the gravitational waves travel in all directions, but including this direction. They go up the throat and around out here and out to the Earth. So we're experiencing gravitational waves from an event that's nowhere near us, if you're just considering distances in our 3 dimensions. And what kind of observatory might be able to detect and measure those kinds of gravitational disturbances? LIGO, that's right, yes! So yeah, Kip Thorne actually says in his talks that LIGO is what detects these gravitational waves. And he actually had an entire prologue to the movie written that described the event and described the detections, and it included LIGO and all this wonderful stuff. And then they said, oh, that's too much science. We can't include that. So they took it out of the film, but he still likes to talk about it. So yeah, we detected this through gravitational waves. Now, one more question I wanted to answer is, can these wormholes exist? What do you guys think? Probably not, actually. Not in nature. They can't exist by themselves. And the reason that they can't exist by themselves is because these things are made of mass, right? They have mass inside our dimensions here, and mass attracts itself. There's gravity, right? So what would happen if you could create one of these black holes is that this throat would immediately close. You need some way to keep it open, to keep it stable long enough for something to go through it. And to do that, you would need to have some kind of negative energy to thread the throat of the wormhole with. And I mean, maybe that stuff exists. We don't know about it yet. Some kind of exotic matter that we can control enough to put it in a place that would allow us to create a wormhole like this, but we just don't have it yet. So the real answer is Maybe. Maybe. So now we can talk about what's on the other side of the hole. And that is a giant black hole. So this black hole, which is a stunning image, and it's one of the iconic images for this film now since it's been out, it's a black hole called Gargantua, that's what they've named it, and it's a supermassive black hole that's at the center of a galaxy that is 10 billion light years away from Earth. So remember how Cooper was talking about the star that was 1,000 years away from Earth? This is 10 billion years away from Earth, if you're traveling at the speed of light. So it's very, very far away. But thanks to the wormhole, we get there in a couple years. And the couple years that it takes is really just for Cooper and his crewmates to get from the Earth to Saturn. The rest of it happens in literally just the span of the clip that we watched, and they're there. So really convenient. So a couple of other things about this black hole, other than the fact that it's 10 billion light years away. It's pretty massive. It's 100 million times the mass of the sun. So you might remember Gabby saying that most supermassive black holes are a lot more massive than the one at the center of the Milky Way. This is an example of one, and it is about the same mass as the black hole that is at the center of the Andromeda galaxy, which is like our next door neighbor from the Milky Way. So this is a realistic size for a black hole in terms of its mass. One of the other things is its physical size, the radius of its event horizon, the place where if you fall in, you can't get back out. And the circumference of that event horizon is about the size of the orbit of the Earth around the sun. So you can see here's the sun, we have Mercury's orbit around here, and then Venus, and then the Earth. And you might be saying, well, does that mean that the whatever this is right here is about Mars's orbit? No. That's a really warped image of this disk of stuff that's around the black hole. And that's related to the next question, and that is, if black holes are really black, if no light can escape them, like Abby was talking about, what is all this light? Where is all of that light coming from? And it's coming from this accretion disk. So an accretion disk is what forms when you have a cataclysmic event, just like the one that Kip Thorne was talking about. In this case, what happened was this black hole ripped apart a neutron star. So if you have a black hole and a neutron star that are orbiting each other really, really fast, and they're losing energy through gravitational radiation, they eventually collide. And the neutron star, in this case, got ripped apart in the process. So some of that material was accreted into the black hole, and the rest of it formed a semi-stable orbit around the black hole. And it's really, really hot. It's very, very hot. So hot that it glows. And that glow is what you're seeing in this light here. So that's the light that goes to all planets. That's sort of the analog to the sun and our solar system for this system of planets that we're talking about in the film. So, what else about this black hole can we talk about? Well, we can talk about really weird things that happen when you get close to it. In particular, we can talk about time dilation. Excuse me? Uh-oh. Are we having technical issues? I don't know. That's an animation, so maybe that's messing it up. Oh, also lens flare. Christopher Nolan really likes lens flare. He has this, he insists that whenever the audience sees something on the screen, that it's as if they're seeing it through the lens of an IMAX camera. So everything has lens flare in his films. He's not as bad as J.J. Abrams about that, though. Let's make a note of that. So can we go forward? Okay, here we go, time dilation. So, time dilation can be sort of summed up in the quote from Kip Thorne that things like to live where they age the most slowly. And if you remember back to that cube grid that I showed you guys earlier, that was similar to the one that Gabby had in her talk, time goes slower when you're close to the mass that's warping the space-time, right? And gravity puts you there. It's really nice of it, right? Nice of gravity, thanks. So the strength of the gravity then, the intensity of the curvature of the space-time, is proportional to how slow time goes in that area. And on the surface of the Earth, we should experience some of that slowing, right? The Earth has its own gravitational field. So how much could it slow down by, right? So say you have 100 years that pass in space, outside of the Earth. How much do you think that the Earth's time is slowed down by on the surface? Anybody have any guesses?
Relative to the distance outside.
Relative to the time that's passing outside of the Earth's orbit.
Yeah, well, I mean, like you have the Earth, and you're rotating this fast, and you're going outside, so you're rotating this fast at the same speed. You're going the same RPM.
No, just the time itself. We're not even talking about orbits or anything like that. If you're just standing on the Earth's surface, time is passing slower for you than it is for somebody who's just standing outside of the Earth's gravitational influence.
Okay.
So by how much? It turns out only by
Only by so many blink lights.
it's only by a second. Just saying. You don't need any more suspense than that, right? So time slows by about a second. And that's a really small change, isn't it? If you have 100 years passing outside of the Earth's orbit, and you go in and somebody who had a clock synchronized to that other person's clock, they would find that their time was 99 years, 364 days, 23 hours. You get the point. It's really, really small. Anyway, Gargantua has a much, much more intense gravitational field, right? So on Miller's planet, for instance, which is really, really close to the black hole's event horizon, I'll show you how close. Time is slowed by how much? Does anybody remember from the film?
64 years?
Every hour is 7.
Every hour is 7 years. So if you spend an hour on Miller's planet, then 7 years pass outside of the black hole's gravitational field. That's intense. That's like absolutely insane, isn't it? This was actually something that was motivated more by the storytelling than by the science. But you can actually have black holes that do this, just they have to be spinning really, really fast. So if you look at where Miller's planet has to be in order to make this happen, so say this is your black hole right here. Your event horizon is pretty far down on this dip here. Miller's planet is like here. It's really, really close. And even then, that orbit is only stabilized if this black hole is spinning at 0.999 times the speed of light. 99.9% the speed of light. So that was a fun thing that Kip Thorne had to calculate for this film. And this is the source of some of the most emotional moments in the film, this black hole's gravitational fields. They get stuck on this planet for about 3 hours. So how long does that mean has passed outside the planet? 21 years. That's right. And in fact, when they get back out of the planet's, well, I guess out of Gargantua's gravitational field, they get back to the ship, and their crewmate who stayed on the ship says, "It has been 23 years." And some change. And if you include the time that it took them to get to Saturn, then it's been like 25 years, right? Since they left the Earth, in Earth time. So Cooper's daughter, Murphy, who was 10 years old at the beginning of the film, she's now like 35. And this is like an incredibly emotional part. I cried. Really, I cry every time I watch this part of the film. And this is really emotional because Murphy she's been so angry at her father for leaving that she never wanted to send him a transmission until now. And she's still really mad. And she says, "This is an important day. It's my birthday. Because before you left, you told me that when you got back, we might be the same age. And now we're the same age." And he's still not back. So what does he do? He goes back into the black hole's gravitational field. And then 50 more years pass in Earth time. And by the time we see his daughter again, she's in her 90s. And again, it's a very emotional part of the film. So knowing these consequences of being inside of this black hole's gravitational field, why on earth would he go back in there? You know he wants to see his kids again. So why would he go back in? Well, the real motivation for this has to do with the premise of the story, that they want to get out of the Earth's gravitational field. They want to launch all humans into space. But how do we do that? I mean, we have some problems, right? We have an artificial colony built. NASA has built the colony already, the station, but it's stuck on Earth. They can't launch it because it's too massive. it requires too much fuel to launch this thing out into space, right? So what's the solution? Turn off gravity for a second, and then launch it up there. And that's a great idea, except that we don't know how gravity works well enough to control it, right? So the next problem is we need a complete formulation of the workings of gravity. And we know really well how gravity works on large scales, on the scales of planets orbiting stars, on the scale of golf balls dropping to the ground, which you've probably calculated 1,000,000 times if you've taken an introductory physics course or a high school physics course. Let's be real, that's super boring, right? Anyway, we know really well how physics works on those scales. What we're missing is how gravity works on really small scales, on the quantum scales. Now, what's really small and has really strong gravity? If you guessed the singularity of a black hole, you're right. So that's why Cooper goes back in. And in that black hole, he manages to get the quantum data, but how can he send it out? He can't, because nothing can leave a black hole. Unless you have a 5-dimensional vehicle and you can leave this way instead of out the top where you came in. So, he gets picked up by a tesseract, which I would really like to explain to you. Please? Do you guys want me to explain it?
Yeah.
See, you've been overruled, Tyler. All right, so I'll try to make it quick, all right? So the fun thing is anybody can build a tesseract. If you take a point, a one-dimensional point, and you move it parallel to itself in any direction, then you create a line. And then if you take that line and you move it parallel to itself in a different direction, you create a square. If you take that square and move it parallel to itself in another direction, you get a cube. And then, if you take that cube and move it parallel to itself in a new direction, if you can conceptualize a new direction, you get a tesseract. So this tesseract is an object that exists in 4 spatial dimensions. And this is really, really useful for Cooper in getting out of this black hole. And what you see in the film is you see him in front of his daughter's bookshelf, and he's like, why am I here? Like, what does this have to do with my daughter Murphy? Well, I mean, the truth is, this is a vehicle that's been constructed by humans, and it's been placed there by very, very futuristic humans who are like, we know exactly what needs to happen, we're gonna put you exactly where you need to be to make this happen. So that's a little bit of like a non-scientific thing, but maybe in the future. So Cooper is in this face of the tesseract, and he's facing this way, where his daughter's bedroom is in this part of the tesseract. Okay, so he's staring at her across this way, and he can't get to her. He can't touch her, he can't talk to her, he can't send any regular kinds of messages to her, because in between here is just the bulk. Nothing gets through the bulk, right, except gravity. And then what's really interesting about this tesseract is that you can also see Murphy in the other parts of it. So if you have her image right here, then light goes from this face of her tesseract part to over here and then in here. So it goes in through the back part, and then Cooper sees it in this face. And then just like the same way, this part of Murphy's face of the tesseract, the light moves across the front face, and then Cooper sees it on this side of the tesseract. And the same thing, if you get light coming up here, then it travels this way, and Cooper sees it on the top. So he sees Murphy from every different angle in here, and it drives him nuts. And then on top of that, the structure of the tesseract is really unique. You have millions, billions, infinite numbers of bedrooms here. And the reason for that is actually also really easy to understand if you think about it in a particular way. So if you could imagine taking a stack of paper. If you have one sheet of paper, that's just like you have a plane, right? A 2-dimensional plane. And if you want to make a cube, a solid cube, you have to stack a lot of pieces of paper on top of each other, right? Maybe, I mean, if they're infinitely thin pieces of paper or just pure geometrical objects, then you need an infinite number of pieces of paper to stack up to a cube. It's exactly like that with this tesseract. You need an infinite number of cubes to make this tesseract. So you have like a really weird, trippy babushka doll of cubes. So that's the tesseract. And he finds that gravity is able to go between him and Murphy. He manages to send her a message in binary through her watch, which is really nice, convenient for him since he gave it to her. And he sends her all the data, she figures out all of the physics, NASA turns off gravity for a hot minute, and they launch all of humanity into space. And it's great, there's a happy ending, it's wonderful. But I haven't touched upon yet the very most important piece in the movie. No, it's one more thing, I promise it's quick. But it's really important, and it's love. A lot of people were really disappointed by this, actually. They thought, oh, all of this really great physics and really accurate general relativity, and then you had to throw love into it? What is this, magic now? But no, it's really, really important. Let me tell you why. None of this movie would have happened if it weren't for love. Cooper wouldn't have left the Earth if he didn't love his children enough to sacrifice the time he could have spent with his daughter in hopes of finding her a home to live out her life in. And then furthermore, Dr. Brand, one of the other crew members, she was pulled toward Edmund's planet because she loved Edmund and wanted to see him again. Even if he was dead, even if there was no chance for her to see him, love still pulled her there. And then Murphy wouldn't have figured out that Cooper was sending her information in code if it weren't for love. And I believe, even though we have a very different set of problems right now as real non-fictional humans, the only way we are going to solve our problems is through love also. Aww. So, love, most important thing.
Alrighty, so we have a few minutes to take questions from Emily. Yes, please.
Does anybody know what determines the size of a potential black hole?
It's not so much the size that matters as it is the density.
I mean a wormhole, not black hole.
Oh.
Very different size.
Size of the wormhole. Well, I guess it probably depends on the mass of the things that form the wormhole, because that determines what the event horizons of the holes are, and then it also determines the curvature of the space-time that goes around the black holes. So my guess is that the mass is the determining factor in the shape, or I guess in the size.
Yes, please.
Can you explain a little bit more about how light interacts with the tesseract?
How light interacts with the tesseract. So, let me go back. Okay, this is good enough. So, if you have one thing in one face and another thing in another face, the light will travel along its shortest path. But in a tesseract, it can only move along these cubes. So it'll go around whatever piece that it thinks is a straight line, which is a cube in the case of this vehicle, and it'll end up wherever that cube leads it. So in the case of Murphy and Cooper, Murphy is right here, so this face of hers in the back right here, light will go from there, around this side, and then to this face of Cooper's side. And then again, it goes, I mean, whatever side you're looking at, the light will go through that face and into the other one. So what you're seeing is light that's been bent.
We've got time for one more question before we have to move on. Yes, please.
Why does the spin of the black hole affect time dilation?
I'm sorry, what?
Why does the spin of the black hole affect time dilation?
That's a really good question. The spin of the black hole, from what I understand, it affects which orbits are stable. So it's sort of like, if, I'm trying to think of like a real world thing that you could consider. I can't think of anything off the top of my head.
You can get closer to the horizon in spinning.
What was that, Johan?
You can get closer to the horizon is smaller.
Yes. The horizon is smaller, is that what you said?
Yeah.
Well, that's convenient. So if the horizon is smaller, then there is an effect on time dilation, because then you can get closer to the black hole where time is more warped. So you can have even more intense time stretching than you would otherwise if the black hole is spinning. You can look up frame dragging of black holes and get some more information on that.